Our next speaker in the series is Czekala. He got his PhD from Harvard in 2016. He then was a postdoc at the Kavli Institute for Particle Physics and Cosmology at Stanford, and is now a NASA Hubble Fellow at UC Berkeley. And in today's talk, he's going to tell us about disks and dynamics of protoplanetary systems.
Hello, everyone. I just want to say thank you very much for the invitation to be here, and especially thank you to the organizers. I'm really, truly grateful for this opportunity to share some science with you all and learn about some really cutting-edge science as well. So today I'll be talking about disks and dynamics of protoplanetary systems. I think we'll have a few more disk planety talks throughout the session, throughout the symposium. But today I'm going to sort of take a deep dive into kind of a narrow topic, but also use that opportunity to talk about some of the statistical techniques that we've been developing that are really enabling us to extract the most information possible from things that we use in lots of types of science, like primarily high-resolution spectroscopy and submillimeter interferometric imaging from arrays like the Atacama Millimeter Array, or ALMA. And I'll talk a little bit about some hierarchical Bayesian analysis work that we did with these disks that sort of helped resolve a key paradox that we were up against, and highlight some of the computational tools that are now being developed that really make this type of analysis much more tractable for more classes of problems. Okay. So to start a talk about binaries, I think it's always useful to just give a brief primer about the many different configurations things can come in. Because if you just start talking about disks or planets and binaries, it's sort of like launching into a regular bi-monthly meeting series. And you really don't know if that meeting is every 2 weeks or every 2 months. But you really want to find out. So typically when we're talking about disks and binaries, most frequently, we're talking about things in this configuration. This is a very interesting configuration. A lot of people have studied this, including many people here. Essentially, there's a lot of interesting dynamical effects that can occur. The outer star can truncate the outer edge of the disk. If there's a planet there, it can pump the eccentricity of the planet. Planet formation is usually suppressed for certain ranges of semi-major axes. In this talk today, I will exclusively be talking about things in this configuration. Circumbinary disks. These are also called p-type disks. And there's also interesting dynamical effects. So classical theories will predict that there should be a truncation around 2 to 3 times the semi-major axis at the inner edge of the disk. These types of systems are also really interesting from a disk evolution standpoint, just basically as a consequence of how steeply stellar luminosity scales with mass. If you take a 2.5 mass star and you split it up into 1 1/4 mass stars, you've really reduced the flux level quite substantially compared to that much more massive star. So it's kind of you have a faster dynamical time scale, but not the concomitant increase in luminosity. And of course, these have been portrayed in the media as Tatooine-type planets or disks. And this is not the reason why I think these are interesting, but okay. So Kepler, which has truly been fantastic for telling us about the exoplanet population, found about a dozen circumbinary planets. These searches were conducted using eclipsing binary stars. So the binary had essentially already eclipsed itself. And then on top of that, teams searched for an eclipse. And so just by nature of that data set, all of the circumbinary planets are in this configuration. They have what we're calling low mutual inclinations, which is the angle between the orbital plane of the binary and the planet or the disk. But nature could also create systems in this configuration. The binary may not eclipse or may only partially eclipse. And the star itself, the planet may even in fact transit a star. It's just that when it comes around the next time to transit, the star that will have transited is moved, possibly out of the plane. And so these transits occur very irregularly, and it's very difficult to search for these things, although a number of teams have been trying in earnest. Just to summarize these graphically, these are the 12 Kepler circumbinary planets, plotting mutual inclination as a function of binary orbital period. So these all have low mutual inclinations, below 5 degrees, and they're all orbiting binaries that have fairly short binary periods, below 40 days. This is just a consequence of Kepler essentially didn't have enough stare time to find things that were orbiting much longer binary periods because there's sort of a stability zone that drifts with that. Okay, so Kepler told us a lot about this configuration. There's a lot of open questions about this configuration. We want to understand this configuration because it's sort of the key to doing all the sorts of analysis that's been done with the single star Kepler analysis, population. We want to know how frequent these stars are. We want to know about their architectures. We want to know all of these properties of circumbinary planet population. But until we really understand this degeneracy, we're sort of probing in the dark here. Okay, so this is how this particular project was motivated based off of the Kepler circumbinary sample. So we said, well, let's look at the circumbinary protoplanetary disks out of which said Kepler planets probably formed. And so let's just look at the population and see how they match up. To do that, we're going to find a binary that has a disk. We'll go and measure the orbital properties of the binary and measure the disk inclination. And then we'll just measure the angle between those two orbit normals. Typically, we parameterize these orbit normals as a sky inclination, little I, and some position angle, usually denoted by the position angle of the ascending node. And it's these two quantities that define the position of the orbit normal in 3D space. And to calculate the angle between the two is just this nice dot product formula. But you need all 4 quantities to calculate the mutual inclination. So for binaries that are a little bit wider than the Kepler binaries, this is possible to calculate these angles directly via a combination of astrometric observations and radial velocity observations. Those quantities essentially allow you to directly measure those ascending nodes and those sky projected inclinations. And in fact, we already know of many disks around these longer period binaries that are dramatically misaligned. So this is a scattered light image from SPHERE of HD 142527. And this is a recent Nature result by Grant Kennedy of HD 9800b. And this is actually a polar orientation. So, so these types of disks are wildly misaligned. And this is kind of a really exciting result for truncating the disk and how material filters through that. But these systems, their binary orbital periods are just much longer than the Kepler planet sample. And so while these are interesting in their own right, they don't really give us much leverage in understanding the circumbinary planet occurrence rate on its own. And so to probe that binary population, those tighter binaries, typically we fall into a regime where we have spectroscopic binaries. So the binary semi-major axis is too small to spatially resolve, but we get a nice radial velocity signal as the two stars are orbiting each other. If we can detect spectroscopic lines of both stars, we can get a double-lined radial velocity solution, which gives us a constraint on this quantity. The sum of the mass of the stars times the sine cubed of the inclination angle. And so really we'd like to go find some stars, measure some double-line radial velocity solutions, and start gaining purchase on their inclinations. But this can be tricky to do for young stars that are active or stars that have a large contrast between their luminosities. And so I'll take a little bit of a detour into some data-driven techniques we've been developing to try to solve these orbital solutions. So keeping the Nobel Prize references, oh sorry, it's the next slide. But before we get to the Nobel Prize references, this is how classical radial velocity cross-correlation works. We have some observed spectrum. In this case, it's a noisy F star. We choose some template. So this could be a galaxy spectrum or it could be a stellar spectrum. We just choose some template. And then we do a cross-correlation against that data as we shift in velocity space. And where we see a peak of that cross-correlation function, that tells us what the radial velocity is at that epoch. And so if we were to do this for 51 Pegasi here, what we would do at each epoch we observe the stars is accumulate a radial velocity. And then with these points, then we'd go and fit a typical Keplerian orbit, parameterized by things like period, eccentricity, argument of periastron, and then derive orbital properties. So this project originated as part of a statistics institute, SAMC, which is in Research Triangle Park. It's kind of a year-long rolling astrophysical statistician collaboration. And I found it really fruitful for addressing some of these problems. So we had some noisy spectra. We thought they might actually be a spectroscopic binary. And we said, well, there's a lot of independent steps here. There's a lot of error that's kind of being accumulated in each step, and it's not really being propagated coherently throughout the whole process. And so if we want to measure radial velocity, do we actually really need a good a priori model of how a star works, or do we really just need a good template? And so we began this project where we decided we could make a template using something called a Gaussian process, and simultaneously solve for all of the orbital properties at the same time. So you're sort of starting from the data set and taking that. You've probably heard of Gaussian processes before. They're all the rage in the exoplanet field. Typically, at least in that field, I see they fall into sort of two kind of categories. At least in my experience, the far more popular one is as a way to model correlated noise. This is some work by Raphael Hayward, where you basically have a radial velocity time series, just like the one before, that you believe the actual radial velocity measurement is being biased due to some stellar activity. And you essentially model that noise with a kernel. And so it's the noise on the measurement is being modeled by that kernel. And we've also done some work fitting synthetic models to data sets where you can actually use Gaussian process kernels to mimic sort of the mismatch between a synthetic model and help alleviate some of the bias that occurs. Sort of another way of using Gaussian processes is essentially like a sophisticated interpolating function. And so this is some nice work by Ruth Angus, where instead of taking a Kepler light curve, fitting a transit, and then modeling the residuals as some Gaussian process, she's modeling the light curve as a Gaussian process, as a quasi-periodic Gaussian process. And it's the properties of that Gaussian process that inform her measurement, which is the rotation period. And so this is kind of in that similar vein, where we are modeling the spectrum itself as a Gaussian process. Gaussian processes, dealing with them, they're simply multivariate Gaussians, just with a lot of dimensions. With computers, it's actually really easy to draw a multivariate vector. You can just use this routine multivariate normal, or if you're an ideal person, you can use m random n. And when you draw a vector, a correlated vector from a normal distribution, this is your likelihood function. It's just a multidimensional Gaussian. And if this covariance matrix is a diagonal matrix, meaning there's no covariance between adjacent points, then our likelihood function is just chi-squared. And so you can see this is sort of a superset of some of the same analysis techniques that we've been using, just we're exploring possible correlations between data points. So what I mean when I'm going to model the spectrum as a Gaussian process, basically I'm making the assumption that the spectrum itself is some random vector that can be modeled as a multivariate Gaussian distribution whose covariance is described by something that we're calling a kernel function. And this kernel function, you can have many different classes. One of the most common choices is this squared exponential kernel, which essentially has lots of covariance nearby, and it tapers off with some decay length, L. And then in this case, R is a measurement in velocity space. So just to give you an example of what this looks like when we draw from a Gaussian process prior, so this is no data, I'm just specifying an amplitude and a length scale. If the length scale is very long, we have draws that have a longer length scale, and you see they kind of oscillate slowly across this very zoomed in region of a shell spectrograph. But if we tweak L to be tighter, then we'll have more oscillations in the same space. If we introduce data, so we use that multivariate Gaussian likelihood, and we build a probability posterior density, we condition on data, what's nice is that same prior distribution will sort of snap to the data. It's constrained by that data to pass through it. And so when you take multiple observations, as is common with radial velocity analysis, you can build up a very densely, very nicely constrained representation of the spectrum. Moreover, you can actually introduce things like calibration effects and sort of self-calibrate your spectrograph to really nail this template down to essentially the photometric precision. Okay, so how are we using this to measure the properties of spectroscopic binary stars? So as I mentioned, in a double-line spectroscopic binary, you see light from both stars at the same time. So at one epoch, the stars may look in composite like this, but as they move in their orbit and their projected radial velocities change, you might have a different pattern. Okay, so to test this technique, we use some data of this nice M4 spectral type eclipsing binary. So we knew the orbital properties very precisely just going in. We had about 10 epochs. So this is fairly good signal to noise. If you're not used to looking at M stars at very high resolution, all of these features are in fact real. They're not just noise. But the fact that they change from epoch to epoch is all the more confusing, which means in fact that you have at least two stars and their superpositions are changing from epoch to epoch. So you get a different realization of the composite pattern. So the goal is to take this and turn this into orbital properties for this system. And this is essentially the problem. So we have our epochs of data here. We want to fit an orbit, which is described by things like the binary period, eccentricity, phase, which tell us the velocity shifts. And then we also want to infer these model spectra. So this is where the Gaussian processes come in. This is the basis set that we're essentially inferring. So when we optimize all of those parameters for this model, this is essentially what your end result is. As we iterate through the orbit, at each time this animation pauses, you see the primary and the secondary Gaussian processes are summed together and evaluated against whatever epoch of composite data that contains. And so this technique, okay, so in this process, nowhere did we introduce synthetic spectra, nowhere did we have a line list, nor did we have to convert from vacuum to air. There's no physics in here besides Kepler's equation. So that's a downside. We do like understanding stars. But if our only goal is to understand the orbital properties en route to then learning the stars, this is one way to sort of bypass the little bit messy part. And in particular, sort of freeing yourself from some of the more difficult aspects of radial velocity work, you can actually attain a much higher precision in some cases. So the black posteriors on this plot, which are generally much smaller than sort of a traditional Todd core analysis that's been used this, you can really tighten up some of the parameters, particularly the mass ratio, semi-major amplitude, and so forth. And one really nice output, if you do care about those stellar properties, is that this delivers those disentangled spectra. So you can, in fact, it delivers a probability distribution over those disentangled spectra that's actually covariant with the two spectra. So you can just paste this on to whatever line transfer or abundance analysis that you want and actually retain the full covariance information in your analysis. And so these are these two M4 stars shown up against other single stars acquired with the same spectrograph. And I think they very nicely lie in this sequence here. I want to point out there's also some nice work by Megan Bedell at Flatiron using sort of a similar data-driven model for single stars, specifically for exoplanet search, called Wobble. Okay, so now that we have a constraint on m tot sine cubed I, let's return to the disk and the total mass. So this is ALMA. If you've seen any protoplanetary disk talks, you've probably seen some great observations of the submillimeter continuum showing these rich gaps and spirals and other types of features. You may be less familiar that certain ALMA configurations also provide exquisitely detailed molecular line information, which we can use to map essentially the velocity field of the disk. So I forward model this velocity field of the disk, sort of using a parametric model that then is ray traced, Fourier transformed, and compared to the visibilities. It's this kinematic fingerprint that reproduces this velocity field that actually allows us to constrain the inclination of the disk and the total mass of the stars that sets the gravitational field. So this likelihood evaluation is done in the Fourier plane, but here's just an example of the data set, our model, and the residuals that look fairly clean. This technique is also really useful if you want to learn about if you want to empirically measure the masses of pre-main sequence stars. This is something that's still sort of ongoing bit of research. These are all of the empirical masses in the colored points that we have today. And you can see there's some regions of the HR diagram that aren't so well constrained. These are important to learn about the types of physics that go into these evolutionary models. In the gray points, I'm showing all of the existing data sets in the ALMA archive that could be used for this purpose. So there's really sort of a tremendous power to use these data sets for auxiliary science. OK, so now we have our double-line radial velocity solution. We have the disk rotation curve. We can divide to get I star, and we compare that to I disk, and now we can measure the mutual inclinations. Great. OK, so we have 4 spectroscopic binaries with circumbinary disks. And they all have I star equal to I disk, or approximately so. What that's really telling us, though, is not that they're coplanar. It's telling us that, so if we've only measured the binary inclination and not the binary ascending node, all we can really say is that the binary orbit vector points somewhere in this red annulus, if we're being honest with ourselves. So halfway through this project, I was like, great, we've done all of these measurements. Let's finally make some comparisons. And it turns out it's not as straightforward as I thought. Fearlessly, I still charged ahead with a Bayesian analysis. And I said, oh, priors. Let's put some priors on it. It'll be good. OK, so here's an example for one system. We really do measure sky projected inclinations to be the same within the margin of error. They really are constrained to be tightly the same. So to calculate the mutual inclination, we need some prior on the position angle of the ascending node. Assuming an isotropic orbit, it's just a uniform prior on the position angle. It could be oriented north, south, east, whatever. Right? Uniform prior. And then you get a posterior that looks like this. Your posterior on mutual inclination looks like this. And this is a little bit disappointing because we're not sure what to do. This is telling us basically we can't say anything other than an upper limit. That's really the truthful interpretation. And it's actually a tricky posterior because maybe you're tempted to say, well, the mode is this value plus or minus 1 sigma. And then you would perhaps wrongfully conclude that the system actually is misaligned when in fact there is substantial probability at coplanar positions. And so this was a little bit puzzling. And so we had a sample of 4 of these systems. And so, well, maybe we can just multiply all of these posteriors together, and that will tell us something. But in fact, that just concentrates this peak. So this really was kind of a perplexing problem. But you can sort of think of like, well, something's going on here, right? Because there must be a conspiracy of alignment, because if we really do measure the sky projected inclinations to be the same for all of these systems, then something's going on with the population, right? Like if this weren't the case, we would have observed some systems that had different sky projected inclinations. And in fact, for this system, there's this really fantastic Nature paper where looking at shadows in the disk, you can actually see the eclipses of the binary on the disk. So it is coplanar. So this posterior is very misleading for this particular system if you only have sky projected inclinations. All right, so one solution to this problem that we arrived on was to treat this problem hierarchically. And you do that by essentially fitting the distribution of mutual inclinations to all systems simultaneously. This becomes the quantity of interest. What is the distribution from which these systems are drawn? So if we parameterize this with an isotropic population, so the binary is oriented essentially randomly in 3D space with respect to the disk, we have a sin I posterior. And this is what the system might look like. And if we had sky projected inclinations of the binary, this would say perhaps favor regions that are maybe randomly distributed or not necessarily favoring one part of this annulus over the other. But if instead we had a mutual inclination distribution that was like this, what this would do is say for each individual system, we're actually going to favor those regions within the red annulus closer to the actual disk orbit normal. Okay, this is called a probabilistic graphical model. You may have seen this in some stats textbooks. I find these diagrams, besides being fun to draw because they're little bubbles and arrows, very useful for thinking about hierarchical models because they sort of give you a bird's eye view of the problem. Just to walk you through this particular model, so this quantity here is called a plate. So every time there's something in the plate, it means we have a variable for a new system, J. And so let's say we have n systems. In this case, we have 4 systems. So J indexes from 1 to 4. D is just our measurements of the inclination of the binary orbit and the inclination of the disk for each system. And our model is going to predict 2 observables, which are, they're cosine I here, but they're equivalent of the disk and the star, and we're going to compare them. So this is the likelihood evaluation, but our model has higher levels to it that are linked together. So this alpha contained within this are those population parameters that describe essentially whether the mutual inclination distribution is more uniform or is more concentrated. And beta is essentially the prior on that prior, which is fixed. And that's basically just showing you that the parameterization that we've chosen here can freely vary between concentrated and more isotropic distributions. And from this is drawn the mutual inclination for that particular system. Okay, I just want to highlight some of the other work we've been doing, primarily with Dan Foreman-Mackey, also at Flatiron, developing some Hamiltonian Monte Carlo techniques that utilize the gradient information of your likelihood function. So just like a function optimizer can do better in higher dimensions when you have the gradient information available, these Monte Carlo techniques can work really well in high dimensionality. So this type of problem might have something like 25 parameters. If you have a system of 10 or 20 disks, now you're talking about 60 or 80 parameters. And these types of techniques work really well in those higher dimensionalities. We've also been putting some of this functionality into a package for exoplanet orbits as well. I had a lot of fun drawing this. I'm sorry to make you suffer through it again. Okay, so I'll just skip ahead a little bit from some of these tests to convince you that, in fact, we're sampling what we think we're sampling. And so what we find is those short period binaries with circumbinary disks are, in fact, coplanar. This is sort of a nice independent data set that really gives leverage to some of the other types of analyses of these Kepler planets that have also been pointing at sort of a coplanar distribution. And so for these systems, for the Kepler data set, this implies that, yes, the circumbinary planet occurrence rate at these binary radii is essentially similar to that around single stars. But as we go to longer binary periods, we see that population that I'd already mentioned, those highly misaligned systems, crop up again. And sorry, on the right here, I'm plotting this as a function of binary eccentricity as well. So mutual inclination versus period, we notice a very sharp transition around periods of about a month, something maybe like 30 to 50 days. Things orbiting binaries with periods shorter than that are almost as a rule coplanar, whereas things longer than that, we now have a wide dispersion of mutual inclinations. Now with eccentricity, the picture is also a little bit interesting. So things that are very circular also tend to have coplanar orbits. And things that are highly eccentric actually have some polar orbit configurations. Just ignore this point for a second. It's GW Orionis. It's actually a circumtriple disk. And so there's some interesting dynamical effects going on there that I think excuse me from explaining it in this sentence. I could talk all about GW Ori if people would like. But Okay, so there's been some interesting work, especially in the last decade, looking at test particles and realistic disks and hydro simulations of disks around eccentric binaries. And there's this exciting result that seems to be borne out again and again, that if the binary itself is kind of circular, the typical type of operation will be that the disk orbit normal will precess around the binary vector, sort of in a mostly oriented fashion. But as the eccentricity of the binary grows, the disk can now start precessing around the eccentricity vector of the binary. And so you can sort of think of this, if you have a circular binary orbit and then you squish it out into a line, essentially, that there becomes a preferred axis for which the disk to orient around. And that opens up these potentially circumpolar orientations. So essentially, disks around binaries, if the binary is sufficiently eccentric, will evolve to either one of these coplanar or polar orientations. But that doesn't really explain why we see this trend with binary period. Specifically, why are all of the disks and planets around short period binaries coplanar? This probably gets at something to do with the difficulty of forming tight binaries themselves. It's sort of been an ongoing challenge in multiplicity studies to actually form these systems. You can't fragment them directly in simulation. And so in fact, they probably fragment further out, and there's some migration process that brings them in closer. So perhaps the same process that brought these systems in closer together, in fact, that brought them into a more coplanar configuration. And maybe at the longer periods, just from the random initial angular momentum from the formation process, maybe there just isn't enough dynamical, the dynamical time scale is essentially too long to bring them into a tighter configuration. So this is some star formation simulations by Matthew Bate. This was a really nice result that came out in Science just, I believe, last week. This is a proto-binary, so a few stages earlier than the types of systems I've been talking about. But you have sort of a maybe 100 AU separation binary here with a giant circumbinary disk that actually extends much beyond this figure as well, but in lower surface brightness. And you can see those individual circumstellar disks being fed from the inner cavity of the circumbinary disk. So this is really kind of amazing, because this, as far as I know, this is like the first data visualizing this thing going on. And so it's before we've really just had simulations or kind of much more sparsely sampled data. So probably something like this is going on in the early stages of binary formation, driving these to those orientations. Okay, so in the last few minutes, I've mostly been talking about points on this graph, and I want to tell you about some of the efforts I and others have been doing using ALMA long baseline configurations to zoom in on these disks in detail to answer some more questions about what may be going on in these actual disks. So this one in particular, this polar disk, this is this Kennedy et al. Paper. It's actually a very tiny disk. This disk is maybe only 3 AU in radius, and it's very old. It's nearly 20 mega years old. And so this is actually one of the few disks that obeys that criterion that I said, that the inner radius of the disk is about 2 to 3 times the binary summer major axis. An interesting other system I've been talking with Ben a bit, he's worked on before, is this TWA3, which is a hierarchical triple system. It's one of these systems here, so it falls at about the 35-day period mark. So it's right on that cusp of things being coplanar and things being polar. So we have ALMA cycle 6 observations of this system. It's actually a very small disk, so this doesn't look like D#, unfortunately, but that's because this is much, much smaller than those disks, even though it's nearby. And the goal of the proposal was to use the exquisite sensitivity of ALMA to actually detect the 12CO emission at high spectral resolution that we can use to do this dynamical analysis. And getting the disk velocity curve is really sort of the key to unlock the entire architecture of this system. There's been a number of teams over the years using adaptive optics, high-resolution spectroscopy, nailing down the radial velocity curves of these systems. But putting these together into sort of this large parameter fit, using those orbital tools I had mentioned, this is sort of like a 35 parameter fit or so that we're working with, These techniques can really tackle these large parameter spaces very efficiently. So in less than an hour on my laptop kind of thing. We're really able to put some tight constraints on the system geometry. Specifically, how close in does that outer orbit come to the edge of the disk? Modeling the ALMA data, how sharp actually is that outer edge truncation of that disk? And so actually being able to test these truncation mechanisms in detail. The last system I'll show is also some recent band 6 and upcoming 7 cycle ALMA data. This is AK SCO. So this is a twin star. They're equal mass F stars. Again, it's one of these eccentric but coplanar systems. Has an eccentricity of about 0.6. And so from the dynamical theory, you would think that in fact, this system would probably be in a polar configuration. But in fact, the disk is nicely coplanar with the binary. Just to give you a sense of scale, this binary orbit is contained entirely within that single pixel in the center of the disk. And so it's a mystery that why is this disk truncated in dust so far out when classical truncation theories would predict that 2 to 3 times semi-major axis. This is 2 to 300 times. And then of course we have the velocity information from molecular species to actually determine the mass of the stars, but also perturbations to that Keplerian velocity field that may be indicative of inflow and other processes. Okay, so just to conclude, so one of our key scientific findings is that there's actually a very sharp transition between mutual inclinations of binaries and disks at around 40 days binary period. Things shorter than that, be they Kepler planets or disks, really do tend to be coplanar as a population. Whereas beyond that, you start to see this wide dispersion of mutual inclinations. This probably is something indicative of something going on with binary formation itself. Some migratory process that actually forms these tight binaries may also serve to orient them. May also be sort of a chicken and egg problem. Maybe it's just that those systems that have been so lucky to form in a mutually coplanar architecture, the migration process is more efficient. And so those are the ones that end up further in. And so I think sort of coming up with scenarios to test this in detail is a really exciting path forward. And so I'll be happy to take questions, and thank you very much for your attention.
Okay, any questions? Yeah, here we go.
If you go back to the system, we can see C13.
Sorry, can you say that again?
Right,
Yeah.
In the 13CO,
Yes.
there's like a line, a bright orange line.
Oh, so this
Outside of this, is that real?
This is just a very faint marginal detection of this. So this disk is fairly old. Ben can tell you more about the lack of disks and so forth, but this really is a pretty faint limit. And so 13CO abundance is less than the 12CO. And so this is a marginal detection. On its own, if we didn't have already the 12CO detection, I would say it's barely there, but just because we have the 12CO, we actually detect. So this is probably tracing a similar region of the outer edge of the disk here. So I would say it's within. Are you talking about this line, or this is probably noise at this point? Yeah.
Jeff.
So I'm glad you asked about this system, because I was also going to ask, it looks like there's a hole in the center of the data distribution, but not in the dust, and that's like counter to my idiot high redshift astronomer's assumption about
Okay.
how fast the dust works.
Well, I think Megan will tell us much more, perhaps, about some of the debate within the community about optically thick and optically thin dust disks. It is ongoing. But so one fear that one might have in analyzing 12CO continuum subtracted data is that if you have a strong dust concentration there, that dust is optically thick. And so 12CO that may be behind that along your line of sight just never gets to your detector. And so when you subtract these two things out, you're left with a residual hole. I don't think that's the case with this system. You can sort of do a geometry check from front side and back side of the disk and so forth. But that is sort of a perennial discussion with sort of velocity perturbations that people discover for planet detection and things of that nature. What is kind of fascinating about this system is, so as I pointed out, this is a fairly deep exposure. I think it's like 2 hours on source or something like that, and it's only 30 parsecs away. So we really are getting down to some fairly deep limits in terms of submillimeter luminosity for the system. If you just look at it with a linear stretch, you'd say, wow, that's a really small concentrated disk. But if you bring the stretch down to the noise limit, you see, in fact, there is this faint halo out here that if we had a scattered light image or maybe some higher frequency observations would probably be more apparent.
Other questions? Juan?
Yeah, so I know that hierarchical Bayesian modeling is very flexible against this. It's just drawing the system you're looking at, but how often are you constraining the posterior distributions of your parameters, I star and I disk, given only 4 systems?
Yeah, that's great, because I get to roll out the backup slide. Okay, so that's a really good question, and it depends really on your data in a very specific way. Because of this spherical geometry that you're looking at in projection, you get these very streaked, very correlated positions on the sphere that can do, I like to call it like the Eye of Sauron plot, essentially. So these are, this is this isotropically drawn fake distribution. So we are recovering the overall distribution itself fairly reliably, I'd say. But if with such a broad distribution, depending on the exact values of the I star and I disk for each system, there's actually a wide range of possible inly inferred values. The thing here that I think is important is that the posterior actually does bracket the value, not necessarily that it's the highest probability value. And this is one of the nice ways that hierarchical Bayesian analysis can use sort of these noisy, potentially biased individual measurements to make a fairly robust inference about the population itself. Yeah, that's a good question. Yep.
Okay.
Does your hierarchical, or sorry, does your Gaussian process code, does it retrieve stellar parameters as well, or just orbital parameters? And kind of as a second piece of that, does it work for single line spectroscopic binaries or stars where there's binaries that it's unresolved, or does it only work for double line?
Yeah, good question. So So the single line case is actually, so yes, you can use just one Gaussian process and use those orbital parameters. If you are in that case, I would recommend using Megan's code because basically the fact that you don't need to disentangle things means you can sort of use a much more cleverly motivated optimization framework that rather than evaluating, those of you that worked with Gaussian processes know the bane of actually evaluating these things for large data sets. They're very computationally difficult because you have to do this matrix solve to. So this is parallelized to do that in a fairly niche manner for a spectroscopic binary. But if you're in the single line case, yes, but I'd recommend using Megan's code for that. And for orbital fundamental parameters, not with this. This is there's no. So one thing this doesn't give you is a systemic velocity because this Gaussian process doesn't have any concept of laboratory wavelengths. But you can take these spectra and then treat them as data essentially with that covariant posterior distribution that I mentioned and use a spectroscopic fitting toolkit to do that. There's many out there. The starfish code that I worked on for my thesis would be one example of what you could do.
Any more questions? Great, if not, then let's thank you again.